Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
Good afternoon. Let's get started, I guess. It's a great pleasure to have Matt Weinberg here. Matt got his PhD at MIT and is currently a postdoc at Princeton. He's one of the young stars in this field known as algorithmic game theory, which is at the intersection of algorithms, economics, and game theory. And he's had some of the biggest breakthroughs in the field, solving some decades-old problems at this intersection. And for this, he won the George Sproul's MIT Thesis Award and the SIG Ecom Thesis Award for work in this area. So thanks.
Great. So thank you very much. Let me start this talk by showing you a picture of what algorithm design looked like 60 years ago. So this is a map of a Soviet railway system at the time. And actually, one of the earliest applications of theoretical computer science was when the CIA asked computer scientists to find a min-cut in this graph. This was during the Cold War, and they wanted to know if they chose to disrupt Soviet supply flow, how to do it as cheaply as possible. So now as we fast forward to 2016, this is a picture of what a more typical algorithm design problem would look like today. And this is a graph of all autonomous systems in the internet. And algorithms run on this graph every second in order to route our internet traffic. So what's the difference between algorithm design 60 years ago and algorithm design today? Well, one thing you'll notice is that there's much fewer nodes in the graph on the left than on the right. So very clearly, the algorithms that we run today, they do need to be much better, and they need to run much faster. But that's actually not the aspect that I want to focus on in this talk. And instead, what I would like to focus on is that in the graph on the left, there is only one central authority that controls all these nodes and edges. These nodes have no interests of their own, and in some sense, they just obey this central authority. Whereas in the graph on the right, these are 42,000 autonomous systems that control the nodes and edges. These nodes have their own interests, and they'll behave in their best interest. They're not just going to do what they're told. OK, so I chose this example because there's actually a famous incident from 2008 where strategic interaction with routing protocols caused a worldwide outage of YouTube. OK, so what happened was, at the time, there was offensive material on YouTube, and this prompted Pakistan to want to censor it. So they asked their internet service providers to update their BGP tables to map from YouTube to nowhere instead of correctly to YouTube. And the outage occurred when this was broadcast to the rest of the world. OK, so what's the point? Is that nobody ran any viruses or worms or malicious code. This is just the way the internet works. OK, so absolutely, Pakistan was deviating from the intended border gateway protocol at the time when they behaved like this. But this deviation was not an attack on BGP, and it was not even intended to cause this global outage. OK, but this problem comes up everywhere. It's not just in routing protocols. And I think the best way to illustrate that is to contrast some traditional algorithmic problems with their more modern counterparts today. So let's start with a classic job scheduling problem. So you have some multitask job, and you want to complete it as soon as possible. So how do you do it? Well, you have many different employees who work for you. And you just need to optimize the completion time by delegating the tasks appropriately. And today, many people don't have their own resources to solve the problems they want. And so instead, we like to crowdsource them. So what's the difference here is that the users of these platforms, like Mechanical Turk, are not your employees. You can't just tell them what to do. So instead, you have to post your tasks in a clever way that incentivizes them to complete them in the first place and to complete them the way you want. And the point is that I suspect people who use these platforms know that it's just a fundamentally different problem when you have to incentivize users to do what you want instead of being able to tell them what to do. OK, as a second example, imagine that you're a major credit card company. And you have a bunch of transactions popping up all over the globe. And you would like to, as quickly as possible, authorize all consistent transactions. So by that, I mean all transactions where no user is overspending their limit. So how do you do this? Well, you have many servers across the globe. You can upload some authorization protocol onto them. And probably it doesn't even have to be very complicated. You can resolve any conflicts using something simple like timestamps. OK, but today, many people like using Bitcoin for their online transactions. And what's the difference here is that there is no centralized Bitcoin authority that is authorizing transactions. Instead, it's a peer-to-peer network that authorizes transactions. And the point is that nodes in this network are not just following a protocol because they're told to. They're all trying to maximize their own income. OK, so now we have to design a more clever consensus protocol that incentivizes nodes in this network to follow it in the first place. And the point is that this is just fundamentally different than when you can just upload a protocol onto a node and know that they will follow it. Okay, so at this point, I hope you're convinced that designing algorithms that interact with real people is fundamentally different than traditional algorithm design. And absolutely, we need to take tools from game theory in order to understand how agents will behave in these settings. And algorithmic game theory is exactly this emerging field that addresses questions like these. Okay, so what I'm going to do in this talk is I'm going to spend the majority of my time describing how to design algorithms that are robust against strategic manipulation, like we saw in the first couple examples. And briefly at the end of the talk, I will also describe how my work addresses other challenges that arise in these settings as well. So for instance, sometimes, because your algorithms are interacting with real people instead of other machines, they need to be especially simple. Sometimes these strategic settings are different enough from what we're used to that we need even new traditional algorithmic tools. And sometimes there are these very specific but very important application domains, such as auctions and Bitcoin, that each impose their own criteria on what makes an algorithm successful or not. Okay, so through the first portion of the talk, I would like you to keep in mind that yes, designing algorithms that are robust to strategic manipulation is one extremely important aspect of designing algorithms for strategic agents, but it's still just one part of a broader research agenda, which is to design algorithms that can succeed in strategic settings. Okay, so let me now dive into algorithmic mechanism design and first describe for you how I think of traditional algorithm design. So I think of traditional algorithm design as being given some input and being asked to produce a desired output. And then what happens in between is what we call the algorithm. Now in algorithmic mechanism design, there's this additional step, which is that you have to first learn the input from strategic agents. And the reason this is interesting is because the agents get some kind of payoff based on the output that you choose. So maybe they will lie about the input if they think it will cause your algorithm to pick an output that they like better. And to contrast these two settings, we call what happens here a mechanism instead of an algorithm. So in a seminal paper of Nisan and Ronen from '99, where they introduced the field of algorithmic mechanism design, and they also won a Gödel Prize for this paper, they asked the following question, which is how much more difficult are optimization problems on strategic input versus known input? Okay, so how much harder is mechanism design than algorithm design? And so the dream here would be to have some kind of black box reduction that could take any mechanism design problem and turn it into an algorithm design problem. So what do I mean by that? Is we'd really like to have this mechanism that works on strategic agents, but maybe what we have is an algorithm that works when the input is directly given. And what we'd like to be able to do is put a black box around this algorithm that we have, so we don't have to understand how it works on the inside, and get this mechanism that we want by just probing this algorithm that we have, possibly over and over. Okay, so the punchline of this portion of the talk is that actually a reduction like this does exist, and I'll give you some more details about that now. But first, I want to quickly motivate why is having a black box reduction the dream? So what are we hoping to get from this? So one reason is that so much more is known about designing algorithms than mechanisms, and that's because we've been doing it for longer. So a very realistic hope is that maybe we can take some of these hard, unsolved problems in mechanism design and reduce them to hard problems in algorithm design, but ones that we've already figured out. Second is that a reduction like this would allow a much larger community to tackle these important problems, and that's because we're taking problems that require the designer to have a sophisticated understanding of game theory and turning them into ones that are purely algorithmic. And last is because these reductions are so heavily structured, we might get a deeper understanding of mechanism design in the first place and be able to at least learn what are good algorithmic design principles when incentives come into play. Okay, so again, the punchline of this portion of the talk is that a reduction like this exists, and we'll also see that it checks all three of these boxes throughout the talk as well. Okay, so let me now start and provide you with a model. So here there's going to be a set of outcomes that the designer can choose from. And there's going to be a set of agents who each have values for each possible outcome. And we're going to say that this information is stored in an agent's type. So you can think of little ti as being agent i's type, and that's a function that takes as input one of these outcomes and outputs that agent's value, which is how happy they will be should that outcome get selected. Okay, now importantly, these types are not known to the other agents and to the designers. They're private information of each agent. But the designer is not completely ignorant about what agent's preferences might be, and he has some beliefs about what these might be. Okay, so as far as the designer and the other agents know, an agent's type is drawn from some distribution di, and only agent I knows their actual preferences, which is this ti. Okay, now the designer's goal is to select one of these outcomes. And if he wants, he can also charge prices to the agents. And now the designer's goal is to do this in a way that optimizes some objective function he has in mind. For example, maybe he wants to optimize what's called the welfare, which would just sum over every agent their value for the outcome that gets selected. Or maybe he wants to optimize his own revenue, which is just the sum of the payments. Okay, so now let's get into the strategic aspect of the model. So the first thing that's going to happen is the designer will design his mechanism. A mechanism has two parts. The first is this allocation rule that takes as input a profile of types and selects an outcome. The second is this price rule that takes as input a profile of types and tells everyone how much they have to pay. After he designs his mechanism, he's going to announce it to the agents, and the agents are going to choose whatever type they want to report. And then the designer will choose whatever outcome and charge whatever prices his mechanism promised. So now how are the agents going to choose a type to report? Well, they're going to do it based on the mechanism that they're playing, and they're going to do it based on their own preferences, and they're going to do it based on whatever they believe the other agents are going to do. But based on this, they're going to choose a type to report in a way that optimizes their own utility, which may or may not be achieved by telling their true type. So now the designer's goal is to, based on this agent behavior, design a mechanism that first encourages the agents to tell the truth, even though they could say anything they want. And this is actually without loss of generality. And second, it should optimize his objective function subject to this. Okay, so the designer's goal is to, over all truthful mechanisms, find the one that optimizes his objective. Okay, so I know that that is pretty abstract so far, so I want to give you a couple instantiations of these. So as one example, maybe that you are a local government and you have a budget to build a new school, and you are trying to decide whether you want to build an English school, a science school, or an art school. So the outcomes that you are optimizing over are you get to choose one of these schools to build. And your objective in doing this is to optimize, again, this welfare, which is the sum over every agent, their value for the school that you build. Okay, and again, the catch is that only the parents of these children know how much they value each school, and they prefer that their favorite school gets built, and so they might lie about their preferences in order to achieve this. As a second example, imagine that maybe you are Google or Bing, and you have a bunch of ad slots that you are trying to sell to advertisers. So now the outcomes that you are optimizing over are matchings of advertisers to slots, and your goal now is to do this in a way that maximizes your own revenue. Okay, and again, the catch is that only the advertisers know how much they're willing to pay for each slot. The advertisers prefer to get better slots, and they prefer to pay lower prices, and so they might lie about their preferences in order to achieve this. So as a last example, imagine that you have a bunch of computational tasks that you need to schedule, and there are a bunch of machines that are willing to process them. And this is actually the same optimization problem that was studied in Nisan and Ronen's seminal work. So now the outcomes that you are optimizing over are assignments of jobs to machines. And your goal is now to do this in a way that minimizes what's called the make span. So this is the maximum over all machines of the time it will take them to process the jobs you assign. This is also the time it will take until all jobs have finished processing. Okay, and again, the catch is that only the machines know how long it will take them to process each job. And the machines prefer to do less work, and they prefer to get paid more, and they might lie in order to achieve this. Okay, so let me now tell you what's known, specifically in terms of black box reductions from mechanism design to algorithm design using these three objectives as a guide. So when the objective is welfare, the state of affairs was actually quite good, and this is due to a seminal series of papers of Vickery, Clark, and Groves. And actually, Vickery won a Nobel Prize in large part due to this work. And what they showed is that whenever you're trying to design the optimal mechanism for welfare, you can do this as long as you have black box access to the optimal algorithm for welfare. So what does their reduction look like? Is first, it will ask the agents to report their types. So in this example, Kostas is saying his value for the bridge is 2, his value for the hospital is 6, and his value for the university is 3. And then all of these types are given as input to an algorithm that works when the input is directly given. And then the mechanism selects whatever the algorithm outputs, which in this case is a hospital. Okay, now kind of the meat behind the VCG theorem is that there actually exists a very clever payment scheme that makes this entire procedure truthful. Okay, but one thing I would like to point out before going on is that this reduction is extremely sensitive to this black box being perfect on every single input. And if instead it's, for instance, an approximation algorithm, what you get out of this reduction is not a truthful mechanism at all. Okay, so there was some recent work by computer scientists that developed a more involved reduction to accommodate approximation. The point is that for welfare, the state of affairs prior to our work was actually quite good. As we move on instead to revenue, the state of affairs is significantly worse. However, we did still know something. What we did know was due to seminal work of Myerson's. He also won a Nobel Prize, in large part due to this work. And what he showed is how to design the revenue optimal auction for selling a single item. Okay, so what did his auction look like? Is first, it asked bidders to make a bid on the item. These bids were transformed into what he called virtual bids, and I'm not going to go into details about this transformation. And then the item is awarded to the highest virtual bidder. Okay, and what I want to claim is that you can view this as a reduction from revenue to welfare, because if you gave me a black box that can maximize welfare when allocating the apple, I could plug into this black box the virtual bids, and then the apple would wind up with the highest virtual bidder. Okay, and again, before going on, I would like to point out that this reduction does extend to when there are multiple copies of the same item. In this case, the second item is just awarded to the second highest virtual bidder. But it does not extend to when there are multiple different items for sale. Okay, so for the 30 years following Myerson's seminal work, despite actually a good deal of effort, we did not learn how to optimally sell an apple and an orange together. Okay, so this table just summarizes what I told you so far, which is that for welfare, the state of affairs is quite good. For revenue, we do still know something, which is in single item settings due to Myerson. But for revenue beyond single item settings, we have no positive results. And for objectives like makespan, we actually have no positive results at all. Okay, in fact, the only thing we do know is an impossibility result, and that's due to recent work of Chawla, Morlica, and Lussier, where they showed that there is no black box reduction from truthfully minimizing makespan to algorithmically minimizing makespan. Okay, so where does our work come in? Is first, we're able to extend this reduction from revenue to welfare far beyond single item settings. And second, we show how to get around this impossibility result by changing the algorithmic objective. Okay, so let me state this more clearly, and this is joint work with Yang Kai and Kostas Daskalakis, is we're able to provide a polytime reduction from mechanism design for any objective to algorithm design for that same objective plus welfare. Okay, so what do I mean by that? Our mechanism will start by asking the agents to report their types. We're going to transform these types into what we call virtual types. Again, I'm not going to give you details about this transformation. All of these types and all of these virtual types are then given as input to a single algorithm. What is this algorithm going to try to do? It's going to try to pick an outcome that optimizes this weird objective. So what is this objective? It's your original objective when computed with respect to the reported types, plus welfare when computed with respect to these virtual types. Okay, and then whatever outcome this algorithm chooses, that's what your mechanism will select as well. Okay, so just to be clear, the mechanism we design is optimal and truthful with respect to the original objective O, but this black box with this weirder objective is a necessary subroutine. Okay, I would also like to point out that this reduction as is already approximation preserving. So even if this black box is an approximation algorithm, what you get out of it instead is a truthful mechanism that is approximately optimal. And also this reduction works in arbitrary settings. It doesn't have to be single item or even multi-item. Okay, so this quote that I like to give that I think puts our result in context nicely is that we now know that transitioning from known to strategic input is no more computationally difficult than adding welfare to your objective. Okay, so the point of this result is not that mechanism design is now easy and we can do whatever we want, because sometimes designing this black box is still hard. But what it does mean is we have a good understanding of how much harder mechanism design is than algorithm design. Okay, and the second result I would like to state is an application of this framework to specifically revenue. And I would like to remind you of Myerson's auction format for selling a single item, where these bids are transformed into virtual bids, and the apple is given to the highest virtual bidder. And what we're able to show is that actually the optimal auction for selling multiple items has essentially the same format. Okay, so what our auction looks like is first, each bidder will make bids on each item. then these bids will be transformed into virtual bids for each item, and then each item will be awarded to the highest virtual bidder for that item. Okay, so there is a difference still between Myerson's auction and ours, and that's in how this virtual transformation is computed. So in Myerson's auction, he actually gave a very nice closed form with nice economic interpretation for how to go from values to virtual values. And in our auction, this virtual transformation is computed instead by a linear program. Okay, so certainly this is a salient difference, and I'm not trying to hide that. But aside from this last bullet, the two auctions do have essentially the same format. Okay, so what I would like to do now is, instead of giving you more details about the proof of this result, is show you some examples, specifically when the objective is revenue and the agents have additive valuations. So what I mean by that is there's going to be n items. Agent I will have value vi, j, for item j, and their value for a set of items will just sum their value for every item in that set. And the reason I want to do this is because I actually think you will get more intuition by seeing these examples than by seeing details of the proof. And it will also convince you that even already just selling 2 items to additive bidders in this quote-unquote special case is already an interesting problem and is worth reasoning about. Okay, so the punchline of this examples is going to be, we'll see that selling 1 item to 1 buyer is actually very simple. The optimal mechanism is deterministic, and it's just to put a price. But as soon as we get to 2 items, now a lot of complexity arises. So first, you have to decide whether or not to bundle the items cleverly. Second, you need to somehow use randomization, whatever that means. And you may need to satisfy these other unnatural properties that will get defined throughout the examples. Okay, so let's start where things are actually simple. That's where there's 1 buyer and 1 item. Okay, so in this example, let's say that my value is drawn uniformly from the set 1, 2. We can ask, what is the optimal mechanism? Well, you should set a price of 1. And with probability 1, I will be willing to pay. So the item always sells. And you will make an expected revenue of 1. And we know from seminal works of Riley and Zeckhauser and also Myerson that this is optimal. If I change the example slightly, and my value is now drawn uniformly from the set 1, 3, the new optimal auction is for you to set a price of 3. With probability 1/2, I will choose to pay. So you will make an expected revenue of 3/2. And again, this is optimal. And the underlying theorem here is that you should always set the price that maximizes that price times the probability of sale. And this is optimal even with respect to much more complex things you might imagine doing, like having some interactive process or somehow using randomization. Okay, so let me go now to the simplest 2-item example I can think of. So there's an apple and an orange, and my value for the items are drawn independently and uniformly from the set 1, 2. Okay, so let's try to reason about what should the optimal auction look like. We can say, well, my value for the apple actually does not change whether or not I get the orange, and that's because my values are additive. And actually, even if you knew my value for the orange, that doesn't give you any information about my value for the apple, and that's because they're drawn independently. So there's actually no dependency whatsoever between the items. So it seems like you should just sell them separately at a price of 1. You would make 1 per item or 2 total. And surprisingly, this is actually not optimal. There's something better you can do. And what you can do instead is bundle the fruits together and set a price of 3 on the whole thing. So what I mean is you should offer me the following 2 options. Either I can get both the apple and the orange and pay you 3, or I can get nothing and pay nothing. And with probability 3/4, I will choose to purchase, and so you'll make expected revenue 9/4, which is better than 2. Okay, so the point is that even when there's no interaction between the items from the buyer side, the seller may still need to consider bundling. Okay, now if I change the example a little bit and have my value for the orange drawn uniformly from the set 1, 3, all of a sudden we need to use randomization. So what do I mean by that? Is you should offer me the following 3 options. Is first, I can pay you $4 and get the apple and the orange. Or I can pay you 2.5 and get the apple with probability 1 and the orange with probability 1/2. Or I can pay you nothing and get nothing. Okay, and this is the unique optimal mechanism for this instance. And actually, things get even weirder if my values for the items are correlated. So we know that there exists a concrete distribution over additive values for 2 items such that the optimal mechanism, the optimal randomized mechanism, has infinite revenue, but the optimal deterministic mechanism has revenue less than 1. Okay, so there is an infinite gap between what you can get with and without randomization already for 2 items, whereas for 1 item, there was no gap between what you could get with and without randomization. Okay, the last phenomenon I want to show you is called non-monotonicity. Let's go back to a single item. And let's say I told you you could sell your apple to one of 2 markets, either D or F. And I told you that F stochastically dominates D. Now I will ask you, would you rather sell your apple to market D or market F? And probably you would think you should sell it to F, and you would be correct. And the proof is actually very simple, because whatever price you're thinking of setting, if you set that same price in market F, buyers are more likely to buy immediately from the definition of stochastic dominance, so you will make more revenue. So what this means is that single item auctions are monotone. So if everyone in market F likes apples more than their counterpart in market D, then you will make more revenue by selling them. Okay, so maybe by now you can see where this example is going, but let me ask instead, if I have an apple and an orange in 2 markets, either D by D or F by F, they're independent, and I told you you could sell your fruits to either market D by D or F by F, and F stochastically dominates D. Then it turns out now that sometimes market D by D yields higher revenue. And this is extremely counterintuitive, but what this means is that 2-item auctions are not monotone. So even though everyone in market F by F likes both fruits better than their counterpart in market D by D, you make less revenue by selling them. Okay? Okay, so what that looks like to me is that this looks like the situation is a complete mess, right? So I don't think there's any reason to hope for a closed form that is somehow going to accommodate all of this bizarre behavior like randomization and non-monotonicity. And what that says to me is maybe we should at least try and design an algorithm to find the optimal mechanism, even if it's a little bit weird, and maybe try to learn something about the structure after the fact. Okay, and so that's what we do, and I'm just going to give you a quick 1-slide proof overview of how we do this. So we start by writing a huge linear program. So this is good because it at least solves the problem that we care about. The downside is that there are exponentially many variables, so we have no hope of solving it. So what we do is we come up with a clever way to rewrite the variables so that there aren't exponentially many, and this at least gives us an LP that we can write down because there are polynomially many variables. Now the downside is that even after doing this, there are still exponentially many constraints. So we need this thing called a separation oracle in order to solve it. It's fine if you don't know what a separation oracle is yet. And then the second thing we have to do is actually design this separation oracle, and this is where more of the hard technical stuff comes. Okay, so first we do have to design some new convex optimization tools. We have to prove some structural theorem about truthful mechanisms, but we show how to use these together to design a separation oracle, which lets us solve the LP in polytime. Okay, and so the last technical thing I want to say on this topic is I'll at least define a separation oracle for you, and maybe this will be useful outside the context of this talk as well. So I think everyone is probably familiar with linear programming, but here there's some convex region P, and you're given as input direction W, and your goal is to find the point furthest in direction W within P. And separation oracles, maybe you're less familiar with, but here there's still a convex region P, and you're given as input a point X, and you need to output yes if X is inside P, or no if X is outside P, and when you say no, you need to output a hyperplane that separates X from P as well. Okay, and so due to seminal works of Kachian and Grocher-Lavache and Shriver and Karp and Papadimitriou, we know that if you can design separation oracles in polytime, then you can solve LPs in polytime as well. And actually, the other direction is true too. And this is called the equivalence of separation and optimization. Okay, and importantly, this is true even if your convex region is defined by exponentially many inequalities. Okay, and the last thing I'd like to say before wrapping up is that our main convex optimization tools are we show how to extend this equivalence to accommodate various notions of error and approximation algorithms. And this is exactly what's necessary in order for our reduction to be approximation preserving. Okay, so I would like to now wrap up this portion of the talk and remind you of Nisan and Ronen's seminal paper, where they asked, how much more difficult are optimization problems on strategic versus known input? And what I showed you in this talk is that we now know that whenever you can design algorithms for any objective plus welfare, you can use those to design truthful mechanisms for your original objective O. Okay, and to give you this quote one more time, is we now know that transitioning from known to strategic input is no more computationally difficult than adding welfare to your objective, and we have a good sense of how much harder mechanism design is than algorithm design.
So if you have k items, you mentioned the example with 2, where one of the things is you offer a bundle of them all, or just them individually. Do you end up with an exponential number of options that you're giving to buyers?
So that's a good question. So it depends on the setting. There's actually one of the very important open questions in our field is exactly understanding how good of an approximation you can get without using exponentially many different options. So we do know there are examples where you need exponentially many options if you want to be exactly optimal, but we don't know if it's necessary even to get like a 1 minus epsilon approximation. Yeah.
You said that the revenue optimal auction is giving each item to the bidder with the highest virtual valuation rate. Is that for any multi-item setting, or is it only for additive?
So that is, okay, so that is for specifically additive. In the multi-item setting, the virtual bids will be much more complex, where they will actually have different valuations for sets of items, and then the optimal mechanism has to allocate the items in whatever way maximizes welfare. And that could be a hard problem. Yeah. Okay. So another thing I would like to say before finishing is that actually Kostas and I were able to apply this reduction to design a 2 approximation for truthful job scheduling. Okay? So why is this important? Well, job scheduling has kind of become this paradigmatic problem for algorithmic mechanism design. And that's because this was the original problem studied in Nisan and Ronen's seminal paper. And now that we have this 2 approximation, this actually matches the guarantee of the best known algorithm for the same problem, which is designed in seminal work of Lenstra, Schmoyes, and Tardosh much earlier. Okay, and I will also point out that we were able to, us and others were able to successfully apply this reduction to other novel problems, such as fair allocation and auctions with budget constraints and more. Okay, and I would also like to remind you of Myerson's seminal work, where he showed that in single item settings, the revenue optimal auction is a virtual welfare maximizer. And a major open question following his work was, what does the revenue optimal auction look like beyond single dimensional settings? And what we were able to show is that no matter the setting, the revenue optimal auction is still a virtual welfare maximizer, just these virtual types might be more complex. So essentially the same format extends to much more general settings. Okay, so I think that those 2 slides put our results in good context with respect to these specific open problems that we resolved. But I would also like to give you some idea for how I expect this to affect the future of auction design. Okay, so one question you could ask me on this front is, do I think Google or Bing will ever use our algorithms off the shelf? And as cool as I think our work is, I would honestly say no. And maybe there are some complaints you have, but one I think is that these auctions are not quite simple enough. So maybe customers will be upset. Another question you could ask me is, do I think big one-shot auctioneers, so for instance the FCC, where there are billions of dollars in a single auction, to ever use our algorithms? And here I would say maybe. And that's because there's this company, CombinedNet, that did run many previous big auctions successfully, and they used a somewhat similar optimization approach. Okay, but actually both of these are, I think, a little bit missing the point. And what I would rather you ask me is, do I expect our work to change how Google and Bing think about designing ad auctions? And here I think the answer is absolutely. And that's because we've shown that instead of reasoning about this very intricately constrained strategic revenue optimization, you can instead reason algorithmically about welfare optimization, which is much more intuitive. Okay, and in recent work with Yang Kai and Nikhil Devaner, we were actually able to show that this same framework not only is capable of designing optimal auctions, but it can be used to evaluate simple auctions, for instance, that Google or Bing could use. Okay, and the last thought I want to leave you with is that if you think about Myerson's seminal work and why did he receive a Nobel Prize, it's not because people are running his auction all over the world. In fact, I suspect no one in this room has ever participated in one. It's because he fundamentally changed how we think about designing single item auctions. Okay, so that's everything I have on algorithmic mechanism design, and I would like to shift gears now and discuss some of my more recent and ongoing work, which I would describe broadly as being resolving algorithmic questions that somehow involve incentives as well. Okay, so in this section, you'll also see some nice traditional algorithmic questions motivated by strategic settings, also some algorithms formally constrained by simplicity. However, at this point, I'm going to completely omit any technical details, and also in some cases even formal statements. Okay, so let me start with peer grading in massive open online courses as one example. And here there are already some very interesting algorithmic questions, which is how do you effectively aggregate noisy grades that come from imperfect graders? And how do you, throughout the course of a class, learn the bias and quality of different graders? And there's already been some really good work on this topic from machine learning. But why this question is interesting specifically to me is because there are also incentives involved. And that's because grading papers takes effort, and students will prefer to do less work and get more reward. But also, students themselves are in the class. And so if the class is curved, then maybe they will lie in order to improve their own grade. Okay, and we do have some nascent work on how to incentivize students to put effort into grading accurately. But actually, what I want to talk about more is how strategic considerations can provide meaningful insight to a different discussion in peer grading. And that's in whether you should ask for cardinal or ordinal information from students. Okay, so cardinal information is what we're used to in terms of grading, where I would take a student and assign her several papers to grade and ask her to put a grade on each one. Ordinal information is not exactly what we're used to, but it's not crazy, where instead I would give a student several papers, or 2 papers, and ask her to tell me which one is better. Okay, and there's actually already some evidence from psychology that says that in crowdsourced settings like these, ordinal information might be better to ask for. And that's because students will tend to produce more accurate data in less time in any setting where there's possibly bias and poor calibration issues. And what I want to argue is that considering incentives is another reason to prefer ordinal over cardinal evaluations. And that's because it is much easier to understand and incentivize behavior when there are only 2 options versus a continuum of options. Okay, so this motivates the following algorithmic problem, which probably at this point looks familiar, is you would like to accurately partition n assignments into A, B, C, etc. using pairwise comparisons. And what's one catch is that maybe these comparisons are going to be erased because you ask a student to compare 2 papers and they don't do it, or maybe incorrect because they just disagree with how you would evaluate them. Okay, and so to keep things mathematically manageable, let's assume that the errors are random and independent across comparisons. So now what you would like to do is, of course, minimize the number of misplaced assignments because the grade should be meaningful. You should also minimize the total work done by the students, which is captured by the total number of comparisons. But also, you would like to be mindful of the physical time until the grades can be decided. Okay, so by that I mean, if you think about how we make conference decisions, we send out one request for reviews, we get the reviews back, and then we immediately decide what should be accepted and rejected. But if you think about these more algorithmic procedures like quicksort, this is pretty interactive. So you would send out a bunch of comparison requests and get the answers back, and then you would decide what to ask next, and then you would get those back, and this process iterates many times. And you can imagine that if it takes a week to get the responses back, that this is maybe unusable. Okay, so there is actually a good deal of prior work on this problem, and it comes largely from 2 communities. The first is a little bit more applied, and here the focus is more on just finding the maximum likelihood ordering when comparisons are given. So in some sense, it removes the design aspect. And the second is from the more theoretical community, where the focus has been more on error-free models, or there are some actually very strong lower bounds known for recovering the complete ordering. Okay, and so what our work does, and this is joint with Mark Braverman and Jiaming Mao, is we first design some very simple one-round algorithms that use CN comparisons and make order n over c mistakes. And we're also able to prove that this is optimal in the sense that any one-round algorithm with the same number of comparisons makes at least as many mistakes. We're also able to extend these algorithms to multiple rounds, improve matching lower bounds, but they're a little bit more technical, and so I don't want to state those completely. Okay, what I will do is give you an example of our simpler algorithms for the special case that I'm just trying to partition into pass and fail, so above and below the median. And let's also say that maybe the comparisons are just sometimes erased, but at least they're always correct. Okay, so what our algorithm will do is first it will pick what we call a skeleton set of size much smaller than the total number of papers. And we'll do all pairwise comparisons within this set many times, enough to guarantee that at least one is not erased. Okay, so for instance, if this set of 5 papers is my skeleton set, I'll do all these pairwise comparisons many times, and then I can definitely learn that 4 is the median of this set. And what I will do now is simultaneously, I will compare each paper not in S to C-1 random papers in S. And if I learn that that paper is worse than 4, then I will fail it. So for instance, if I learned that 2 was worse than 3, which was worse than 4, I can fail it. If I learned that it's better than 4, I can pass it. So if I learn that 8 is better than 7, which is better than 4, then I can pass it. But if I don't learn either, I have to just guess. So if I learn that 5 is better than 3 and that 5 is not as good as 9, that doesn't immediately tell me how 5 compares to 4, so we have to guess, and this is where most of the errors come from. Okay, but just to remind you, we're able to show that this algorithm makes order n over c mistakes, and this is optimal for any one-round algorithm with the same number of comparisons. Okay, so let me give you another example in this domain, which is designing incentive-compatible tournaments. So what's the motivation here is that match fixing and throwing is still actually a huge problem in professional sports. And sometimes this is because of gambling, and I don't know that I can say anything intelligent about this. But sometimes actually matches are thrown in order to improve a team's performance at that same tournament. Okay, and there are two very famous instances of this. One was actually very recently at the London 2012 Olympics, where 4 badminton teams, including the world-ranked number 1 and the world-ranked number 3, were all disqualified for throwing matches. And longer ago, actually this happened in the World Cup too, where 2 prominent teams colluded to fix their match, and they actually both benefited from the match result. Okay, so what happened at London 2012? Well, they used the same World Cup group stage format. And group stage tournaments, it turns out, are not what's called monotone. So what that means is that sometimes losing a match in the group stage might improve your chances of winning the tournament because it gives you easier matches in the single elimination stage. And there are many tournament formats that are monotone, for instance, just a single elimination bracket, where it's clear that getting eliminated is not going to help you eventually win the tournament. Okay, now you can read the citation for why these teams were disqualified, and essentially it's because they weren't trying their hardest. Okay, and my own opinion is that I do think the tournament designers are at least partly to blame, and that's because they took these athletes that have been working their butts off their whole career to try and win an Olympic medal, and they put them in a tournament and said, you are more likely to win a medal if you lose this match, but you're not allowed to do that. You have to try your hardest to win anyway, right? So like, what do you expect athletes to do in this situation? Okay, now what happened in the World Cup is that group stage tournaments actually have another problem, which is that they are manipulable. So what that means is that sometimes 2 teams can fix their match to improve the chance that one of them wins a tournament. Okay, and there do exist tournament formats that are non-manipulable, but they're all a little bit silly. So for instance, if I just picked a random country and said, you are the World Cup champion, this is not a manipulable tournament format, but it's also not very exciting. Okay, so why do we not know better non-manipulable tournament formats? Well, it's not because we didn't try hard enough, it's because there's an impossibility result. Okay, so I think a good tournament format should at least be consistent in the sense that whenever there's an undefeated team, this team should win the tournament. Okay, but there's an impossibility result that says that actually every consistent tournament format is also manipulable. So what that motivates us to do, and this is joint work with John Schneider and Ariel Schwarzman-Kohenka, is we define a notion of approximately manipulable. So we say a tournament is alpha manipulable if sometimes 2 teams can collude to improve the probability that one of them wins by alpha. We show that every consistent tournament is not only manipulable, it's also 1/3 manipulable. But a single elimination bracket with random seeding is exactly 1/3 manipulable. So this is optimal. Okay, so kind of the corollary of this line of work is really if you're concerned about match fixing and throwing, you should be using single elimination brackets. Okay, and the last thing I want to talk about in any detail is what I would call auctions for everyday people. Okay, so the motivation for this is that I do think the mechanisms that I described for you earlier in this talk are manageable in the sense that if the FCC chose to, I do think they could use this to sell spectrum, but they are not what I would call simple in the sense that I don't think I myself could run this mechanism to sell my old Pokemon cards. Okay, but if you remember from the examples, we learned that even in ridiculously simple settings, the unique optimal mechanism might be pretty complicated. The good news is that at least for special cases, we have not yet ruled out simple but approximately optimal auctions. Okay, so very quickly, the model is there's one additive buyer and one seller with n items, and the buyer's values for the items are drawn independently. Now, one simple way to sell the items is you could just post a price on each item separately and tell me to take whichever set of items I choose. Another simple way for you to sell the items is you could just post a single price on everything together and tell me to take everything or leave it. Okay, but there actually is still some bad news, even with respect to approximation. And we know that there are instances where selling everything separately is a bad idea. And there are also instances where selling everything together is a really bad idea. But what we're able to do and this is joint work with Moshe Babayov, Nicola Morlica, and Brennan Lucier, is we're able to show that actually for all instances, the better of selling separately and selling together gets you a 6 approximation. Okay, and in follow-up work with Aviad Rubinstein, we're able to extend this result to a much more general model of buyer valuations that are what's called subadditive instead of just additive. Okay, so as a corollary of this line of work, this means that if you sold anything on eBay recently, probably you did do it in a way that is provably approximately optimal. Okay, so what we saw in the last 15 minutes are what I would say are examples of really interesting algorithmic questions that also involve incentives. And I just wanted to very quickly touch on some other directions like this where my research has recently gone or is currently going. And so one instance of this is understanding what are called information cascades in social networks. And what works like these try to understand are answers to questions like how do opinions spread in social networks. Another example, if you remember from the beginning of the talk, is understanding incentives in Bitcoin security. And here the idea is that in this peer-to-peer network, it's not that there are some nodes that are honest and some nodes that are malicious. It's that everyone is strategic and everyone is trying to maximize their own revenue. So there's kind of like a new paradigm for security and distributed systems that come up in settings like these. Okay, and there's actually so many aspects to auctions. I didn't get to talk about all of them. One is learning in auctions, and so this has 2 flavors. First is maybe the auctioneer has very limited information about the bidders, but wants to design good auctions anyway. And second is maybe the bidders are playing the same auction every day, and they need to learn how to bid optimally. Okay, and the last example I would say are just any algorithmic platforms that somehow involve incentives. And peer grading we saw is one example of this, but there are so many more. So for instance, if you think about ride sharing like Uber and Lyft, or online dating, or reputation systems like Yelp or Airbnb, and there are tons of these. And the point is that even though the designers of these systems have been pretty successful so far, no one really has any idea what the right thing to do is in these settings. Okay, so something I'm really interested in doing in the near future is trying to lay some good foundational theory that can be applied to domains like these. Okay, so this is the end of my talk, and I hope that I've convinced you, if nothing else, that designing algorithms that interact with real people is fundamentally different than traditional algorithm design. And I also hope I've convinced you that my research has successfully addressed some of these novel challenges that arise, and that continuing along this path is absolutely the right way to design algorithms that can succeed in strategic settings. So that's it. Thanks a lot for listening.
Any questions?
Could you give intuition as to why you need the random seeding in the tournament for it to be?
Sure. So let's say, for example, maybe there are like 3 stars in the tournament. And let's say maybe, let's say it's me, you, and Anna. And let's say we all know I'm always going to beat Anna. Anna is always going to beat you, and you're always going to beat me. So if we know ahead of time the seeding, and let's say you and I are going to play each other first, and the winner is going to eventually have to play Anna, then I already forgot. Then I guess it would be our incentive for me to win our match because I can beat Anna later, whereas you would naturally win. So we need the randomization because we don't want to, it's better if we don't know exactly who we're going to face in the end.
Okay, well, let's thank Matt again.
Yeah, thanks.